Hello, hello. Just gonna do some devlogging. I think maybe I have a path forward to make a game, so I'm gonna try doing regular logs as long as I don't get a job. If I get a job, then I quit devlogging and I start working for money. But in the meantime, I can just do some logging, make some risks, and have some fun. So, continuing on my video from last time where I was showing off my ability to render lower resolution images and accumulate multiple frames over time into a high resolution image that you can then present to the player either the full resolution, or you can downsample it to the screen resolution if it's a really high resolution. Continuing on that, I also revived an old project of mine where I was doing a form of ray tracing. This was 5 years ago. The big hype thing back in the day, and I think is still kind of hype, is doing voxel ray stepping. So you would have your grid of all your light data, and you can go ahead and go through that light data one little Minecraft block at a time. And the result of that is you get this the reflection. You can clearly see these blocks, but I can do, since it's ray tracing, I can just scatter the light farther and farther. So in the scene view, I'm not doing any sort of temporal accumulation, but once you're in game, I can blend multiple frames together. So in this case, here I'm actually, what I'm doing is I'm blending frames together, but I'm doing so at a sub-resolution space. So what I'm actually rendering is much lower resolution than what you're seeing, and it's accumulating up to the native resolution. And it'll be clear why I'm doing that in a second. So it's like, okay, this looks kind of nice. It's a little bit blurry, it's a little bit smeary. So what's the benefit? Well, of course, since this isn't screen space, if I focus on this column, you think that with a column, with screen space reflections, if you no longer see the column, you would no longer see the reflection of the column. But since this is ray tracing, real ray tracing, you can still see the column. You can see the sky. The blue area there is the sky, and it's being occluded against this wall, so you get pretty much realistic lighting. Yeah, and I'm doing so in the most high performance way I can, using this tiny resolution for actual rendering and accumulating everything, because you may notice that I'm getting 700 frames a second. So the resolution for this capture is 1600 by 1200, so this is still higher resolution, I think, than 1080p, just the way that I'm recording with OBS. So this is with a 1080 Ti graphics card. Or no, sorry, I have a Vega 64. I sold my 1080 Ti while mining was hot. And mining is still hot, so I should have sold it later. But so we can take this build on this memory card, and let's pick something a little less overpowered. A Vega 64, it came out as a competitor to the 1080 Ti. Didn't quite succeed in being quite as fast. I was hoping that the driver overhead was less, but I think in fact the driver overhead for a Vega 64 is more. Actually, that laptop is not going to work, since it doesn't survive when it's not plugged in. And I have lights plugged in, so I can't do that. I need more power plugs, that's the story. So this is my HP Spectre. It's an Ultrabook. It's very thin, and it has integrated graphics. So I'm just going to log in. And let's see, can I operate this upside down? Probably not. Let's see. Let's go to SD card. No, we're not going to operate upside down. Go to one of my builds. Run that sucker. Let's see if this works. So this is running off a battery, so this isn't going to perform as well as it does when it's plugged in. But I'm going to try it anyway. So this is 720p. Oh, and of course I don't have a frame counter up, so I need to get one of those up to prove something. Something tells me I'm going to have to get into video editing. Alright, so I got Fraps open. Oh, so there we go. So this is Intel Integrated Graphics, 720p, and I was getting 700 frames on the Vega 64, and on Integrated Graphics I'm getting a happy 70 frames per second. So, you know, Integrated Graphics is 10 times as slow, or it's more than 10 times as slow, because the resolutions are quite different from each other. I think probably this is probably casting at least half the amount of rays as my desktop is right now. But we're still getting above 60 frames per second. And I was looking at this. I started testing this 2 days ago. I was excited. I was like, how is this possible? Integrated graphics doing any semblance of ray tracing. You know, and of course it's fuzzy. You can see it's very stochastic looking, but the fact is it's actually doing ray tracing. So my next step that I'm trying to work through is to get this working on a phone, and it's not done, and that's kind of the body of what I wanted to try and record is working through how to get it working on Android. And there's some major problems with that. So let's shut off my laptop. And I need to, so on Android, the big problem is it seems as though Unity refuses to render with deferred pipeline. Unity has a built-in deferred pipeline, and that's what I'm using for this. The game writes the geometry to a whole bunch of different full-screen G buffers, one for diffuse color, so whether things are green or purple or brown, and then there is one for normals, the directions of the surfaces, so that when you actually apply lighting to it, you can get different kinds of lighting, you know, across a sphere, you know, different magnitudes of color depending on the direction of the surface. The problem is, yeah, Android doesn't seem to want to do that. So instead, I am in the process of working on a custom deferred renderer. This is the result of that, and it's pretty garbagey. But the successful thing is that I'm writing to two separate G buffers, which Unity refuses to do on Android. I don't know why. Writing to two separate G buffers, one for color, or sorry, three. One for color, one for specular diffuse, and one for normal and depth data. I need all three of those, and I might need a fourth for motion vectors, but I'm not there yet. Of course, I got a lot of work to do. So, yeah, we got lots of work yet to do on that. In the end, having my own custom deferred rendering pipeline will allow me to just have more control and wrestling control away from Unity and into your own hands seems like always the best bet. Like there's a new URP pipeline and universal rendering pipeline and the HD rendering pipeline, both of which are a little bit tricky to integrate with because you have to make sure that all of your additional effects layered on top of the rendering pipeline are fed into compute buffers. And so compute buffers is the only language you can communicate to these rendering pipelines in order to add additional features. And because of my temporal upscaling and the ray tracing together, like both these things are fundamentally change what you're doing with rendering, and aren't so much layers as they are steps of a pipeline, then it justifies making my own rendering pipeline. is my thinking. So I was a little bit behind on Git just to showcase things in the editor, because jumping forward, things get a little bit crazy. Uh-oh. Ooh, I want to hold on to that. I don't want to lose any of this stuff. Regardless of the fact that I'm recording, I do not want to accidentally discard things. Yeah, I want to keep that. Let's see. Okay. So I'm on master, and I forgot to commit a shader that was just untracked. So I'm going to go ahead and amend an existing commit for that. Oh, thank goodness I didn't discard that. That'd be very upsetting. Okay. So let's get rid of fraps. Yes. Oh my goodness, this is going to be so much editing. Maybe I just won't edit. That would make me happier. All right, let's reload. So as part of my custom rendering pipeline, I have to have custom shaders, which is why everything looks so flat. Everything is directly rendering to the scene view what it would render to the G buffers right now. So the first of the G buffers is diffuse color. So everything is just declaring its diffuse color to the scene view. It works. Like, I don't necessarily need a perfect render coming out of the scene view. Game view is currently black. And why is that? So I have custom deferred rendering on. Oh, but the composite shader is no longer in existence. I hope it is in existence. Let's see, custom deferred. Aha! So it works. Alright, let's save that. And again, I need to get into making sure that I commit things right when I make them. So that works. Yeah, that's what I was showing off on my Android phone. I confirmed that you can write to multiple G buffers in a shader. Let's check out that shader right now. Okay, so this is the shader that will actually render the G buffers. It takes in multiple G buffers, does some silly lighting on it, and then blends the silly lighting with your diffuse color, and that's what you get out of this. Very naive. It's going to change in the future. So the one that I was unsure whether or not it would work on Android, because Unity refuses to support the name's not coming to me. Refuses to support that kind of render pipeline, is writing to multiple G buffers. I'm doing that by having a struct called pixel output that has these diffuse, norm depth, and spec smooth. Zoom in. Whew. And how do I X out of this? So it gets gets some bump map data, and it initializes your pixel output. It can write to the diffuse, the norm depth, and the spec smooth, and just return the whole thing in that struct. That is how I am outputting multiple things, and it works. The on the CPU side of this custom deferred behavior, I am kind of trying to work on a declarative style for things. I'm hoping that in the future this is going to help me refactor things better. So I am declaring my own dictionary that takes an enumerator as the key and provides a description of the texture as a value. So that diffuse has this description, normal depth has this description, and I'm specifying render order because dictionaries don't have a guaranteed order for when you enumerate through them. So once I have this description, then every time I'm rendering, which is too often, but for now it's fine, I'm going through all the descriptions, and I'm using link, which is very handy. It generates garbage, but I'm hoping that it won't generate too much garbage, and also that the garbage collector in Unity has gotten better. We were struggling a lot with garbage collection at my old job. In Unity 5, we basically had to make sure every single system that generated garbage instead pooled its own data using lists, and it was nightmarish. and you couldn't use Link. So since I've upgraded Unity from Unity 5, I'm using Link in good faith. So we're going through all descriptions. For each one of these, we're getting out the enumerator, text names, and the description. If anything about the texture, which I'm trying to retrieve from the textures dictionary that also takes a text names as the key and return to render texture. If anything has changed or doesn't exist, then we're going to release the existing texture if it exists and make a new one. And we're going to return a key of the name and a value of the texture so that you can put that into a dictionary again. Every single frame. It's not super great for garbage, but we're not doing it that often, and it just makes things hopefully more refactorable later on, because it's very dry. I don't have multiple places where I'm checking all these width, height, format, and depth for every single texture. It's only happening in one place in the code. So that's nice. Hooray for Link. After that, I get to set the target buffers for the camera. It's like setting the render texture for the camera, except you can set multiple things. So I'm going through all the descriptions again, setting the order of all the keys and values. This is important. This is why I have the render order, so that things go diffuse, normal depth, and spec smooth, because once it gets to the shader, that order is inferred or implied. And then I get the colored buffer for each one of these textures, given the name is the key, and that is my list of color buffers. And then I get the depth buffer from whatever I set the depth buffer from to normal depth, which has a depth value, and then I should be writing to that camera, or I should be writing to the textures from the camera. Yeah, and then once we have the camera rendered, then this is a kind of a screen space effect that happens after the camera renders. It can create the composite material from the composite shader, and the composite material sets textures for each one of these textures. It can just provide the name of the texture and then the texture itself, and loop through all of them so I don't have to set them all manually. And then I do one little blit from source to destination. The source doesn't matter because I'm just using the textures that I specify, not main text. So just one little blit, and then I get to have this little naive shading solution. That's it, and that's what works on Android. So in order to get lighting working fully as I've shown off, like the thing is, I want to know whether or not I can do ray tracing on a phone. My HP Spectre, it's not exactly a powerhouse in terms of its graphics card. But according to FutureMark, or it's a benchmark, I'm not sure if it's FutureMark, but it's got a score of like 80,000, and equivalent on my phone gets a score of around like 30,000. So being able to get 80 frames per second at 720p should be the equivalent of getting around 30 frames per second at 720p on a phone. And of course, since phone screens are very small, I can probably even pick a lower resolution than that to maybe get 60 frames per second, possibly, but I'm not 100% on that. So I've confirmed that I can do G-buffers. I need G-buffers. The reason I need G-buffers is for optimization more than anything else. I could have it so every single triangle that you're rendering does ray tracing right then and there, because the source of the light, like how it's casting the rays through, that data is already generated as this big 3D volume. So I could do it right when the triangle is rendered. The problem with that is that if you have a lot of different layers, say in the case of like a tree, trees have all these leaves, and they may render front to back, which is good, because if you have a tree behind another tree, if you have a leaf behind another leaf, and that leaf is rendered after the one behind is rendered after, then you won't have, like, the pixel will be immediately not like depth cold. It'll check depth from the previous leaf, and since it knows that its depth is farther away, then it will just not bother doing any of the shading, any of the colors, nothing. Won't sample any textures. All it does is does the initial depth check and be like, I can't do anything, and continues on. That's good. The worst case scenario is if you have a model that happens to render all of its triangles from back to front. Then you render a leaf, you shade it nicely, it's very expensive, and then you throw that all out because you have to render a leaf in front of it, do all of that fancy shading. Oh, and then you throw out all of that because you have a leaf in front of all of that, and do all the fancy shading, and whoops, there's a giant wall in the way, and you have to throw everything out for the whole entire tree. So you can solve this by spending a lot of time messing with the order of your triangles. It's not perfect. I had a thing where for a tree model you could over time generate 6 different meshes for the same tree that have different orders of all the triangles, and it works. It's just memory expensive, and takes CPU time. So anyway, we could do all that, or we could use G-buffers. I've opted to use G-buffers because what happens with G-buffers is regardless of order, all your data gets drawn to the screen for color, normal. It's very cheap because all it's doing is just drawing that data and doing nothing else. And then after that, the lighting can come along and do some shading given that flat G-buffer. No longer are you worried about throwing out any of your work because the color data that is there, all the spec norm data that is there, is guaranteed to be shown to the user. So you're not wasting any work by the time you shade the G-buffers. So we got the G-buffer. Now I need to prove that I can do all the voxel stuff on Android. So I need to figure out the cheapest way to do random read-write to a 3D texture. That's kind of big problem number 1. Big problem number 2 is viewing a 3D texture. I feel like viewing a 3D texture is the one I should worry about first, and then random read-write, because once I random read-write, then I can view it to confirm that it actually works. So I'm going to do this as naively as possible to start, and then refactor later. Of course, this code's so beautiful, but if you have beautiful code all the time, then your code never changes. So we have to make it ugly again in order to get stuff done. So I'm just going to start just going here. We'll set a new texture. Call it test volume, and provide test volume as it. We don't have a test volume yet. So we're going to make a new texture 3D called test volume. It's going to have a very small width, height, and depth. Texture formats of ARGB32 because that is the most common type of texture. And what other constructors are there? MIP chain, I don't know what that is. MIP count, we're going to do 0. Is there any other places where we're generating a 3D texture? No. So we're just going to trust that this works. So in order to generate a volume really quickly, I'm going to go ahead and set all the pixels. 32, because we can just set the color 32s of all those pixels. This takes an array of colors and a MIP level. So we decided that this is going to have 0 MIPs, so the MIP level we're going to pick would be 0. And the colors that we're going to provide would, we'll just do I still haven't figured out how to do ranges in link, so we're not going to bother with that. I'll keep the Googling to a minimum. You know, this is a great way for me to try and focus on this stuff. Keep the Googling to a minimum and just try and logic through a really simple solution. For int x, for int y, for int z. We're going to write to every single part of this volume. We're just going to reduce the amount of magic numbers by setting a variable. And here's a fun little lesson. If you're looping through more than one dimension of a multi-dimensional array, counterintuitively, you should probably loop through the z's first, the y's next, and the x's last. The reason for this is that generally memory is laid out so that all of your x's are together, and then the next set of x's are together for a different y, and once all the y's are done, they're together, and then the next set of x and y's are there for the next z. So if you want to be really conscious about how you're accessing your memory, you should probably have the x be the innermost loop and the z be the outermost loop. Or if you're doing 2-dimension, then the y would be the outermost loop. So we need some colors. New color 32 array. Dimension cubed. We're going to set each one of these. So since this is a flat array, it's not multidimensional, but we're going to pretend it's multidimensional. First dimension, just going to specify it there. The next dimension, y, we're going to say is y times dimension. Next dimension would be z, dimension squared. And we're going to set this to either black or white. I'm going to just say that if the modulus of x, x modulus 2 is 1, then we're going to provide a new color 32. And I think this comes with defaults. We can say white or color. Okay, that's just color. Color 32 doesn't have any fun static defaults. So we're going to say white. Otherwise, use a color 32 of black. Even though it's black, it still is opaque, which is why this final thing, the alpha, is always set to 1. Alright, so then we can set pixel 32 for colors. And yeah, I don't know. There's a better way to explain why this is how it is. You can look it up. Alright, so we should have a test volume that is striped black and white on the x-axis. So we set that to the texture. We can confirm that it runs. No compiler errors, no syntax errors, no runtime errors. That's good. So this test volume name, I now have to take in the composite shader. And what's the most naive way to start sampling from this? Probably I would just use IUV again. IUV is the UV space for a screen, where 0 is on the left, 1 is on the right, or 0 is on the top, 1 is on the bottom. I think. Yeah, I'm pretty sure that's how it works. We can just do that. Instead of text 2D sample, we can do a text 3D sample, given our test volume, which is a sampler 3D. And with the UV, That's in 2 dimensions, so we can cast it to a 3D float, but we should probably specify an additional value for the Z. X and Y are here, Z is here. And this is test volume sample. Comment out the previous stuff and see what that looks like. It is white. Cool. Alright, now we get to stare at the code and debug. If we run it, that doesn't change anything. I can confirm that we're actually getting some... Oh, you know what? First thing, there's so many gotchas with this stuff. For whatever reason, after you set pixels, you have to apply. Pretty sure. So let's do that. Aha! We already have something. Awesome. That was it. So just make sure after you do set pixels, you apply. Okay. So we have a little bit of black. We have a little bit of gray, black and gray. So I don't know why it isn't just white. But we can, you know, really crank it up to show it off. Oh. I wonder if it's doing that because color 32s are taking integers. Is that the case? Oh, bytes, yeah. Okay. So, there's how it should look. Let's recompile. Okay. Good, good, good. So, I know it works. I know it works in Windows. And this is like the Android Unity. So if I go to build settings, it's set to Android. And, you know, so the game view is kind of emulating Android in the sense that I no longer have the ability to use my mouse and keyboard, which really sucks. Something about how the input works, it just disables mouse and keyboard. Regardless of the concept of using a mouse and keyboard on Android is still possible. They still disable it, I guess, so that you're forced to just start developing your touch controls. So we know it works in the editor, but there's no guarantee that it'll work once you get over to the phone. So I just need to find my cord I was using to plug this in. So Android development, you have to have developer mode enabled, and you have to be able to transfer data through USB. There's like an option in the developer mode settings. Okay. So now it should be hooked up, and then hopefully I just hit build and run. And the run part of that for Android is going to be transferring it over to my phone, and it'll kill the current execution of the current demo, and it'll load up the new one. And I'm hoping I'll see some black and white stripes. If I don't, I'll be very sad. But here's hoping, because if I can validate that I can sample it from textures, then I can, you know, do my ray stepping through the 3D volume, which is good. But I still do need another thing of being able to write to those textures, because, you know, I won't be able to have a volume over my entire game. My game, I'm hoping to make a big open world game. So the volume has to be regenerated whenever you move around. I don't want to have all that running on CPU. I want it to happen in either a compute shader or a fragment shader. Both of those things can do random rewrites to 3D volumes, at least on Windows. So we'll see. So it's building the Gradle project. Just going to check if we're still recording. We are still recording. And let us see. How are we doing for time? 35 minutes. Oh my goodness. Okay, so it loaded up. Hey! That's a good sign. So we got black and white stripes. That's sampling out of a 3D texture. Oh, that is good news. That is real good news. So, here's the next problem. Like, once I validate these two things, then I'm basically like ready to build a open world puzzle game. I want it to be a puzzle game on Android because puzzle games on Android work really well and they're easy to do one-handed. If you have an action game, you have to have two hands basically. Unless it's in 2D and it's like a single button game. And so if you ever played The Witness, The Witness is a full 3D game and has 2D puzzles. It looks beautiful and you enjoy the environment, but ultimately the core gameplay involves doing these puzzles. There is no like skill tests, there's no timing, except for the last puzzle is like this crazy gauntlet where you have to complete a bunch of randomly generated puzzles. But for the most part, like it's relaxing, you're just working on these problems and you're solving these puzzles, and between puzzles you get to look at this cool environment, and the aha moment is starting to see forms of the puzzle within the environment, like at certain angles things line up where you see a circle and then you trace out a line from that. It's really cool. The Witness from 2016. So I'd like to play off of that, make an Android game kind of like that. Of course, I don't want to make the puzzles very complex because there is an unserviced genre, in my opinion, of making games that are easy to play, but also are really cool. There's games that are easy to play, like a lot of idle games, but not ones that are very dignified and have good graphics and things. So I want to slip in there and see what I can do. So I've proven that we can see the volume. So basically I need to take this and turn it into a compute shader to figure out if I can write to the volume. So I'm going to go ahead and create a new compute shader called test volume writer. Click in there. By default, you know, you have all these threads that things happen on. So I'm going to go try so that given 1x, you know, and a whole bunch of y's and z's, we can brute force write something to a 3D texture. The result, the XYZ of which, it's been a while since I've done compute shaders, honestly. We're going to get rid of this. I'm going to just make it work the same. I think I can do the same logic where it's branchy, which is why they don't recommend doing this in shaders, is branches and shaders can be a little bit scary. But we're doing it anyway, just so that I can have a parallel between the code. So if the modulus is 0, then we're going to return white. And white in floats for colors is 1. 1 is the maximum color, unless you're in HDR, generally. And then otherwise, we're going to return black. Still have an opacity of 1, because we're not doing clear. That should be it. That's all you need. So random read and write texture in 3 dimensions. Alright, so how do we actually use this? So in custom deferred, we now have to reference the shader. Not a buffer, a shader. Test volume writer. And before I get too far ahead, I'm going to go ahead and hook that up so I don't randomly puzzle as to why it isn't working. I'm like, test volume writer. All right, save that. So instead of doing all of this, we're going to do something different. So we're going to say test volume is now a new render texture where the, let's look through all the options here. So width, height, depth, that's a little counterintuitive because the width and the height will be the dimension variable I specified, but depth I'm going to keep 0 because that's just talking about the kind of the Z depth for occluding triangles against other triangles. It doesn't matter. The format will keep basically the same, except we have to say render texture format is ARGB 32. MIP count is 0. Now, additionally, we have to tack on to say that the volume depth is dimension. So it's really silly, but it's just something you have to remember because it's just another silly gotcha. If I want to make that a little bit more compact, I think I can do it that way, just so that it's part of the same initialization for test volume. And so we've created the render texture. Now we have to render to said texture, so we can take the test volume writer and dispatch it. With the first kernel index, there's only one function, so there's only one kernel. Kernel index starts at 0. So thread groups is tricky. Oops, copy this, paste that. So what am I doing here? Let's just make it easy. So we're going to say that the number of threads that can work on this shader is 4 in each dimension. So if we have 4 threads running in each dimension, then we only need to say that there's one thread group per dimension, because each thread group has 4 threads associated with it for a total of 4. And since the dimension of our render texture is 4, then 1 times 4 is 4. So it's going to render to the entire texture. So we're going to dispatch that. But I didn't bother assigning the result. Test volume writer texture, set texture. Result is the name that is in the shader, and then we're going to provide the test volume. Oh, we have to specify the kernel index. It's happy now. A cool thing to note for me in the future, it's not really relevant to anyone else, but you can also specify the MIP level. So if you want to generate your own MIP maps, you can do so using your own compute shader. That could be really cool in the future. I have plans for that, but it doesn't matter right now. We want to render to the first MIP level. For now, there's no MIP maps to worry about. So that should be it. I don't think we need anything else. So we should write to it, and then we just immediately read from it, and it should work the exact same. Let's see if it works first time. It did not work first time. Invalid kernel index 0 passed must be non-negative less than 1. Well, let's look at the error for the above. That one is just noise. It's stupid. This one's the actual problem. Attempting to bind texture as UAV without UAV usage flag set. I think what it's talking about is we need to enable random read write. So hopefully that works. So now it's gray. If we clear, we can run just to make sure that it's actually running. Result has mismatched output texture dimension. Expected 3 got 2. Huh. So even though I set the volume depth to 4, it's still thinking that it is a 2D one. It's pretty strange. So let me find other examples in my code. I got lots of code to reference off of, so I should be able to figure this out. So, sorry, I have to say it's a volume. And possibly create it. Is volume true? Volume depth, enable read write. Apparently that's obsolete. Dimension. What does it take? Texture dimension. Okay, text 3D, sure. Okay. So let's see if that works. I'm guessing it won't. Yeah, I think I do have to say test volume create. Oh, that's good news. I mean, for Windows. So it's not good news yet until I can get it running on Android. So we're just going to immediately build and run this. My phone's still plugged in. It should still find it. It's looking for compatible Android devices. Found it. Starting its build. So the iteration time for testing on Android isn't that bad. I started testing by like manually copying builds over to Android once they were done building, and then installing it in Android. And Google is very distressed about that because it thinks that you're going to be compromised. But it's like, it's my own build. Shut up. But yeah, this makes it a lot easier to just build and run. Once it's plugged in and you have I think it's called ADB enabled, USB ADB, then you should be able to iterate relatively quickly. I mean, these builds still take some time to make the textures over and over again, make the shaders over and over again, and building Gradle project is very inconsistent. All right, let's see what happens. So let's see. Uh-oh, this is a problem. So it's black. I was afraid of this. So yeah, if I can't random write to 3D textures, then am I screwed? Maybe. But I don't know. There's a lot of learning in there. So I'm going to have to figure out why this is black as opposed to, shaded, white to black. I don't have a lot of hope that it is in fact possible, and I just forgot about something. I'm thinking I might have to try some other techniques to render to a 3D volume, and or just do it in CPU. But we'll see. I think it might still be possible, but I'll have to try random write to a 2D texture, because I could still build up a series of slices to make it 3D. Or I could try writing to a 3D texture, but doing it per compute shader thread would write to a single determined point on a texture. That could still be doable for writing to a texture. So we'll see. Yeah, we'll see what's possible. But I think the recording's over. You kind of see the problems that I'm dealing with. And yeah, we'll leave it at that. So have a good one.